Hi Chemistry, this is Mrs. Ellsworth. This is the second video of Unit 3 talking about atomic theory, but now we've gotten far enough along in our atomic theory that we need to understand some of the experiments that scientists were doing to understand how that relates electrons to light. Anyways, to understand light, we've got to understand a couple properties or characteristics of waves. And this is a good diagram showing the wavelength. Now, wavelength is designated with a Greek letter, a Greek symbol called lambda. Okay, and it's the distance between a crest and a crest of a wave. And it's probably easiest to measure it crest to crest, or it could be trough to trough. If you have been in math and you understand sine curves, you know where else that they can be measured from. Now, if this water was at rest, this would be the at rest point. Anyway, we could measure the amplitude of the wave from the rest position. And that with light, that would tell you how bright that the light is. Now, if it is coming in faster, notice that the frequency is occurring faster, so we've got a shorter wavelength. Okay, then that would also tell you the color of the light too. Now, frequency is measured in hertz or per seconds, and wavelength is measured in some type of distance unit like nanometers, meters, centimeters, and so we'll discuss that here with the electromagnetic spectrum. Now, with the sun has all of these different types of waves coming from it. Anyway, there are other types of sources that create these type of waves too, but let's go ahead and look at this. The lower energy wave has got a long wavelength and it has a very low frequency. And then as we get up into the higher frequency wavelength, the higher frequency and the shorter wavelength, because you've got shorter waves coming in faster, okay, we notice that's got more energy. In fact, these ones are here if you're on a cordless phone in a metal building. You'll notice that they can't carry the waves around things. In fact, sometimes in a metal building, radio has a tough time getting in. We have to have some type of receivers to help us hear from them. But radar can go through. Microwave can go through them too. And somewhere in here at 1900 hertz is where actually the cell phones are delivering their messages. Anyways, we can keep on decreasing that wavelength and increasing our frequency to where we get to just below red, which is called infrared, below red. Okay, and then we get to our small little bit here that's the visible light spectrum. Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. And then just above violet is ultraviolet. Okay, and then we still get more energy into these waves, and they're getting shorter, they're penetrating more. This can penetrate into your skin and cause you to get burnt. And X-rays actually goes through tissue, perhaps even through bone, and this is going through a lot. Anyway, so as there's more energy into the wave of the electromagnetic spectrum, it can penetrate further. Now, there are some ways that we use this information. Notice I was saying as one goes up, the other one goes down. As the wavelength gets larger, the frequency goes down. But what happens is that they always come to the same exact speed, which is the speed of light. And that is 3.00 times 10 to the 8th power meters per second. And this, no matter where we were on the spectrum, when you multiply the two together, you're going to get 3.00 times 10 to the 8th power of meters per second. So all these different wavelengths travel at the same exact speed, the speed of light. Now, light we were just talking about right here travels in waves. But they were finding some other findings. And we're going to be doing this tomorrow, where we will look at different gases and tubes. And these gases will perform a certain color. But when we look in a spectrometer, we actually see that, hey, they are at very specific wavelengths. Okay, and that is showing us that also light comes not only as waves, but very discrete particles or line spectra. We say that this is either continuous, like waves, or else discrete, and they're going to be called photons that come at very specific measurements. Now let's talk about continuous and discrete. This is going down at a continuous. You could be at any height, but at the steps, they are discrete. They only go up certain steps. You can only be so high, you can't be in between steps. Now that's like shoe size. You've got size 8, 8.5, 9, 9.5, and so on. You can't, but your feet sizes are definitely continuous. They're in between them. Anyway, waves are continuous like our electromagnetic spectrum. It traveled from very big wavelengths to very small wavelengths, okay? And photons are these little packets of light, okay? And they are discrete. There's only some, you can't do a half a photon or anything like that. They're at whole number ratios. Max Planck used lots of experiments to prove how light behaves with photons. Okay, so we know that light travels in discrete particles called photons and also continuous waves, but maybe also electrons behave that way. And that's where we're getting a lot of these physicists who are doing these experiments, and this is how it's going to tie into our new atomic theory. Anyway, so now thinking about the electron, they were doing several different tests. One of them was the photoelectric effect. If you would have certain light waves go and strike certain kind of metals, then they would get an electric current from it. So this is a certain amount of light, and it depends on the color. Like cesium can only do certain wavelengths, and if you did a different wavelength, then it wouldn't necessarily produce an electric current. So they were learning that different frequencies, specific frequencies that of light was going in there, and that would produce an electric current. So that's talking about more of particles. So anyways, there's more ideas with this. They're saying, well, why do hot objects glow? Because this is the problem. Without the quantum theory, we don't have any way to describe how we are getting this energy to glow. So Max Planck, the scientist, he decided that if hot objects are going to emit light, okay, then we need an way to understand these small packets of energy that it's releasing, these quanta. Anyway, so oh, by the way, quantum is singular, quanta is plural. Anyway, he came up with a formula where he even figured out a constant, so you could figure out the frequency, and you could multiply it times this constant. We'd figure out how much energy had to be put into an object to make it glow, or else how much energy would come out of it. Now, Albert Einstein, he went and took this idea, and if it wouldn't be for them understanding photons, so much of the things that we use today, like my garage door opener, or I should say my garage door, if you are opening it or closing it and your feet go past that little path of light, it'll stop it from going down. That's the photoelectric effect. They are catching little photons on a receiver, and it is making a current go through there with the photons. The photons are making a circuit complete. Anyway, electromagnetic radiation can be absorbed by matter in whole number photons. So that means that electrons are discrete particles. We've always thought of the electron, whenever we've talked about it in the past, being particles. Well, then scientists were doing other experiments with light, okay? And then they started doing them also with electrons. Now, what happened is that they were throwing electrons through a double slit barrier, and what they were expecting is that if they're particles, that they're going to go and they're going to show up on the screen back here in just 2 spots. But it's just amazing what really did happen. What happened was that they got slits, they got electrons detected even between the slits. And that was amazing, because this is a pattern for something we know, waves. Okay, and so they knew that pattern. And I found some excellent diagrams to help us understand. Here's a canal with some waves that's going through, and there's a double slit barrier here. And what happens as this water goes through here, it creates waves that go in circles like this. Okay, and then here's that double slit again. And then now look at this. There's interference. Here's constructive interference, where it's building a bigger wave, and destructive interference, where it's kind of taking all of the wave away. It's dampening it. Okay, looking from above, we've got constructive interference, destructive interference. And so they're noticing as it goes and it hits a barrier, this is the pattern that waves create when you've got a double slit. So that was exciting for scientists because they knew from this example right here that not only do, from the photoelectric effect, not only do electrons behave like particles, but this is showing, hey, electrons are actually waves too. Okay, and that will lead to much more discovery with a new quantum theory. And we will discuss that in video 3-3.